I can't see any, so let's thank the speaker again. Yes. So, Daya, please. Can you share the screen?
Yes, I can hear you. I hope, Bit, I'm audible to you.
We can hear pretty well, so
Okay,
you
so
just
okay, that's
to
perfect.
share the screen and
Okay, that's great.
okay. So can you share the screen with your presentation, please?
Yes.
Great. Okay, so the last speaker of this session is Daya Shankar Kulshreshtha, and we will speak about quantization of Fermionic Schwinger model.
Okay, so I hope I can take off. Good. So, a very, very good afternoon and a very, very good evening to everybody. And my heartfelt thanks to the wonderful team of the organizers, my great friends, with Milo, Vladimir, and Mate. All of them are extremely efficient and sincere, I must say. For the younger ones, I cannot hesitate in praising them. It's a praiseworthy work that they are doing, and it's very, very impressively going on. All right, so I think I can now come to the topic of my talk for today, and this is on the quantization of Fermionic Schwinger model. So by Fermionic here, I mean Schwinger model, people are very well aware. Fermionic originally, in fact, it was written down in Fermi fields. So instead of considering it in the bosonic fields, I would consider it in the original Fermi fields. So you see the Schwinger model, it's commonly called as Schwinger model. It's in fact the vector Schwinger model, which is really known as the Schwinger model. But Schwinger model can be a chiral Schwinger model, it can be a vector Schwinger model. So I would, in a few minutes, I would explain the difference. But when vector is not used, then usually it refers to the vector Schwinger model. So, okay, so this model actually describes a two-dimensional field theory, a two-dimensional quantum electrodynamics of massless fermions. So the fermions are massless, m into psi bar psi term would not be there. And in the vector Schwinger model, what happens is that the left-handed and right-handed fermions are coupled to the U1 gauge field A mu, which is the photon field, with equal couplings. And whenever these couplings are unequal, maybe slightly, or then that would be a chiral Schwinger model. So right now I am going to, because it's a class of models actually, so I am going to consider only a vector Schwinger model. And the model is characterized by its exact solvability, a property which is really ensured by a remarkable feature of one-dimensional fermion systems, namely that there is a correspondence of one-dimensional fermion fields and one-dimensional canonical fields. And this issue was settled in the 70s actually by Lenny Susskind, Kogut, and many others, hosts of theorists around the world. So what happens that for example, the Dirac-Lagrangian could be given by some terms in terms of the bosonic field, which happens to be the kinetic energy of some boson field. Similarly, the vector gauge current and the axial vector gauge current, they also could be expressed in terms of the bosonic fields. So this boson fermion equivalence, in fact, as far as I know, it works perfectly well for two-dimensional field theories, but I'm not so sure if it has been established for higher dimension, 3 or 4-dimensional theories. But so anyway, the two-dimensional theories by themselves are very important, and if they are written down in bosonic field, they become a little bit easier to solve, and they really provide a laboratory to test and develop several theoretical ideas. And in fact, quark confinement was proved convincingly in two-dimensional field theories only. Now, let me write down the model itself. So this model here, it's a generalized model, generalized Schwinger model, in the sense that this definition that I am giving here, it defines vector model as well as the chiral Schwinger model. So now the action of the theory is defined in terms of the fields, fermionic field psi and psi bar, and the bosonic field A mu, which is the U1 gauge field A mu. So this is just the functional form. It consists of, this is the kinetic energy term for the electromagnetic field A mu, and this is the well-known Dirac-Lagrangian, but these models are in two dimensions, so one space, one time dimensions. So mu will take on value 0 and 1 only. So this is the famous Dirac-Lagrangian, and these rho matrices are just the gamma matrices of Dirac. They are expressed by rho mu. Here they are two-dimensional Dirac matrices. And you find that there is a product of this psi and A mu here, sitting here, even psi bar, along with these gamma matrices or the rho matrices, and a coupling coefficient ER. So that means, and this is a similar, another interaction term, here the only coefficient is different. This is ER and EL. So ER and EL, they express the coupling coefficients for the product of these three terms, psi bar A mu psi, psi bar A mu psi, but in between you have these rho mu times 1 plus rho 3 and rho mu times 1 minus rho 3. Now let me first define the conventions of my calculation. So F mu nu is the usual field strength of the electromagnetic field, d mu A nu minus d nu A mu. Everywhere mu nu take only two values, 0 and 1. And this is the metric tensor that I am going to use. The coupling coefficients ER and EL could also be recombined into a different form, like G1 of EL minus ER by 2 and G2 EL plus ER by 2. So if we set EL and ER to be equal, then equal to, let us say, E, then G1 would be 0, and this would correspond to the vector Schwinger model. So what would happen? These rho 3 terms from here and here, they would cancel out, and the other remaining two terms would add up. So and whenever EL and E are slightly unequal or completely unequal, whenever they are unequal, then that case corresponds to the chiral Schwinger model. So now further, this psi bar is the Dirac conjugate. Psi bar is the Dirac conjugate, and it is related to psi dagger, which is the Dirac adjoint. So the Dirac conjugate and Dirac adjoint, they are related through this rho 0 matrix, and these two expressions are conceptually the same. They look algebraically different. If you multiply them, rho 0 here and rho 0 here, we will find that rho 0 square is minus 1, so you get it minus iota times psi dagger. So I choose these particular matrices for the rho matrix, rho 0 and rho 1, and in fact there is a small motivation for this, is that the string theorists and the people working in supersymmetry, supergravity, they eventually do work with the Fermi fields. So so it is their choice, and I renormalized my calculations to them. So rho 0 is this, and rho 1 is this, and one has to check that these row matrices, they must satisfy the Dirac algebra, where anti-commutation relations of rho nu is minus twice eta mu nu, where eta mu nu is defined by this. Oh, we need not be confused. We must always consistently check our things. This would look to be plus here if my notation for eta mu nu were different. If I choose minus 1 plus 1, then this will have to be plus 1. So one has to be careful. Okay. The only thing while dealing with the Fermi fields is that there is a possibility of several minus signs occurring from many places, and this one has to watch out. So rho 3 is the analog of gamma 5, but there are only two matrices, rho 0 and rho 1, and therefore I write it rho 3, which is rho 0 times rho 1. And you find that this rho 3, in fact, this rho 3 is the chiral operator of the Dirac theory, gamma 5, analogous to gamma 5. So its square, you can check, is the same matrix times this matrix times the same matrix. So this would be a unit matrix. So it's a unit 2 by 2 unit matrix. This is a very crucial expression here. Rho 0 square is minus 1 and rho 1 square is plus 1. And therefore the inverses of these rho 0 and rho 1 matrices, they exist. Okay. And if one were today, I would not be working with the light front quantization of this theory. But if one were working with the light front quantization, then one will have to construct rho plus minus matrices, where you will have to take linear combinations of rho 0 and rho 1. And then what happens that the inverses of rho plus minus do not exist. So there is a different formalism for that, which is due to Philip Mannheim, Peter Loden, and Sten Brodsky. And I think last time I had used it in my talk, but right now I am working only with the instant form quantization and not light front quantization. So I do not need rho plus and rho minus. So I need rho 0 and rho 1, and their squares are non-zero, and therefore their inverses exist. And this is fine. Well, this I need not highlight, but I mean chiral operators, you can through projection operators you can use this. So chirality for a Dirac fermion psi is defined through the operator rho 3, which has eigenvalues plus and minus 1. Now I summarize the last two slides into this slide once again, specifically for the case EL equal to ER equal to E. So in that case, though the terms that were appearing in the Xn and that involved rho 3, they now drop out. So these terms and these terms, one is coming with plus, one is coming with minus, they will drop out. And so you are left with only one E, which is equal to EL as well as ER, because this is the vector Schwinger model. And so this is your usual Dirac Lagrangian, this is the kinetic energy of the electromagnetic field, and this is the interaction Lagrangian. So in fact, we are talking about the QED theory. It's a two-dimensional quantum electrodynamics theory, where this is the proper interaction term. Now, let me, after defining the vector Schwinger model, let me try to construct this model from more basic fundamental beginning. Namely, let me consider the Dirac Lagrangian. And you see, this is the standard Dirac Lagrangian, but I have written it in two dimensions. And one can check what kind of a symmetry this theory has. And this theory is seen to have a global symmetry. So psi goes to exponential of minus iota some epsilon, some gauge parameter times psi. But this epsilon is a constant. It's a constant phase. And because the epsilon is constant, and therefore this transformation is global and not local. So I would like to have local transformations. Obviously, theories with local transformations are more rich in physics contents. So there is a standard procedure due to Neoders. How to gauge? This is called as the gauging the global symmetries into local symmetries. And here I would like to gauge the global symmetry of the Dirac-Lagrangian, which is given by this, into a local symmetry like this. And obviously I can add the corresponding term for the transformation of the electromagnetic field standard. And so then I end up with a QED theory. How do I do it? This is a standard procedure that in the first place I have to replace the partial derivative del mu by a covariant derivative d mu, which is defined through this. Plus or minus is your choice. It does not matter physics wise. Physics remains the same. So first step is to introduce the covariant derivative in your action under consideration, which is the Dirac action. And then that theory would then involve electromagnetic field or U1 gauge field as well. However, it would not be dynamical. So I must add the kinetic energy term for this U1 gauge field, and that is this. And now when I substitute the value of d mu, then I get these two terms, is the interacting QED theory, back to the same chiral vector Schwinger model. So I think with that sets the scale for that defines my model properly, and then analyzing it becomes easier. So I have two pieces in my Lagrangian or the Lagrangian density. I sometimes use it for Lagrangian or the Lagrangian density, but calligraphic symbols are always densities. If you integrate them over the entire space, you get the Lagrangian. So this is the bosonic part, and this is the fermionic part. This is the Dirac-Lagrangian. This is the interaction QED Lagrangian. And we have seen them in two different ways that they must be like that. All right. So the fermionic Lagrangian, for the later convenience, I would like to split it into two parts or just rename them. So this is the Dirac-Lagrangian and this is the interaction Lagrangian. I further would highlight that the Dirac-Lagrangian could be written alternatively, equivalently in two different forms. So what happens if I find the difference of the two, if I calculate the difference of the two, I see that this is a total divergence. So this is the Lagrangian density for if you are writing the action, then you have to integrate it over the entire space-time. And then this total derivative term, d mu, j mu would simply vanish, and therefore theory would be completely invariant. Okay, completely. So now, they would be identical. Okay, the total derivative term would disappear, and these two theories, they would give the same physics. That is what we will see in the subsequent slides. Now so I write this L1F now, and I write this as L2F. Interaction Lagrangian I have separated out. So this is the same, it stays the same. This I am doing on purpose because I want to obtain the canonical momentas from here and from here. They would look algebraically different. But I will show at the end that the physics does not change. Physics remains the same. So my complete Lagrangian is sum of the two, bosonic plus fermionic. This is the bosonic part, which I have written in the component form to be like this: 1/2 del 0 a1 minus del 1 a0 whole square. And the Fermi part of the Lagrangian could either be L1 or could be L2F. I would work with both of them, and at appropriate places I will show their equivalence. So we also need a line element or the invariant length square. So in the finite form, this would be S square, which is eta mu nu x nu. In the component form, it becomes x0 square minus x1 square. And this the same expression but in the infinitesimal form. So this is in the infinitesimal form. Metric tensor is then set. It is the same for both of them, which is +1 and -1. And it has been the same when I wrote down the Dirac algebra for the row matrices. It was just the same. Okay, so perfectly fine. Now let me write down the canonical. Let me write down the canonical momentas obtained from L1 and L2. First of all, I write it down for L1. So pi 0 is 0 and pi 1 is non-zero, and there is a velocity here del 0 time derivative of a1. So this will not give me any constraint. However, this gives rise to the Dirac primary constraint pi 0 equal to 0. Now let me see what happens with the fermionic part of the Lagrangian. First I work with L1f, which is this form, and if I take the derivative, as I said, because of the Fermi fields, we have to watch out if we receive what are the places from where we are going to receive minus sign. So if I take time derivative of this term, this del 0 psi has to be shifted here. It has to cross psi bar and I pick up a minus sign. And here there will be del 0 of psi. So I accordingly obtain this result, which equivalently could be written as a minus of psi dagger. And pi bar, as you see here, this is the derivative time with respect to the time derivative of psi bar. And there is no term here that has del 0 of psi bar. Here, if you give mu the value 0, then this is time derivative of psi. But there is no time derivative of psi bar, so this is 0.
Daya,
Yeah.
you have 5 minutes.
So, okay, I speed up. So these are the two constraints that I obtain in this theory. And if I demand that the constraints be present in the course of time, then I would get the Gauss's second constraint. Now, so by looking at that, it is clear that pi and pi bar are behaving like independent fields because one cannot be obtained from the other. The same is true for psi and psi bar. They are behaving as independent fields. And if I do that, so these are the constraints in this case. Now I go to L2f and I find that this is -1/2 of psi dagger. And this is, now in this case, the pi and pi bar could be obtained from each other. So in this second formalism, these are pi and pi dagger, and they can be obtained from each other. So, and what you have is this is pi plus, I'm missing a psi dagger here. I'm sorry, there must be a psi dagger here. So this is the first constraint and this is the second constraint. Now one has to watch out with the definitions of the Poisson brackets for the Fermi fields and for the bosonic fields. One has to look for this sign. And what happens, the fundamental fermionic Poisson brackets for psi and psi are the same, whereas they differ by a sign, minus sign for the bosonic fields. I go to the Legendre transformation and write down the canonical Hamiltonian in the standard way, and this part I can skip. So this, I think I have explained that in one L1 case, the psi and psi bar, or pi and pi bar, or psi and psi dagger and pi dagger, they are behaving as independent fields. Whereas in the second case, they behave as, so what is the physical meaning of this? That in the second case, this suits really the Majorana spinor fields. Majorana particles are the particles that are antiparticles of themselves. So there is the physical meaning to it. So I again summarize the four constraints in these two cases, and I calculate the matrix of the Poisson brackets of in these two cases, and this comes out to be identically the same in both the cases. And so its inverse would also be the same, and the gauge fixing choices would work fine because I have only one set of them. So A0 and A1 equal to 0, time axial gauge and Coulomb gauge. This gauge could also be written as del 1 A1, and I have checked it mathematically that both yield the identical results. Now this matrix becomes 6 by 6 and it could be inverted. Its determinant could be found, and therefore I could write down path integral as well as I could obtain the Dirac brackets, non-vanishing Dirac brackets. So this is perfectly fine. So this matrix is invertible, and therefore this is the, I invert it, and this is the inverse of this matrix, and this looks everything fine, and this could be now directly used for the. So here I obtain, I have written down the equal time commutation relations which are non-vanishing in this particular theory. In fact, there are only two results, this and this. The last three results are really identically the same. If you convert the variables psi bar into psi dagger, you obtain this, or if you use the definitions of canonical momentas, you obtain this. So the last three expressions are just the same, and this is A1 with E1 is this. And mind it, if we choose different gauge fixing conditions, then this result might be different. So it depends on the choice of the gauge. Okay, and well, so I will finish in time, don't worry. So now I could go to the path integral quantization and make a transition to the quantum theory by writing the vacuum to vacuum transition amplitude from time t equal to minus infinity. One vacuum, this first vacuum is at t equal to minus infinity, and this second vacuum is at t equal to plus infinity. So the entire spectrum is covered, and then you can write down it using the standard forms. I have not shown further details of this, but all the phase space variables have been taken into account, and the functional measure, because I have been dealing with two cases simultaneously. So in one case, the functional measure is given by d mu sub 1, and in the second case, it is given by d mu sub 2. Now, there is a very important observation. You see, these symbols are called as weak equalities. They were defined by and introduced by Mr. Paul Dirac, none other than Mr. Paul Dirac. And what they mean, if pi 0 is weakly equal to 0, it means it is strongly equal to 0 only on the hypersurface of the constraints. Otherwise, it is non-zero in the rest of the phase space of the theory. And the same thing applies to each term, all of them. So when I solve this path integral, it would become very transparent to you that results in both the cases would be identical. For example, you write 2-point function, 4-point function, n-point function. Then so here I have just defined this weak equality symbol, and I have explained what is this weak equality symbol, and this actually would lead to the, so this I think I have covered already, but this needs to be covered, yes. So the two path integrals, even though they look algebraically different, but they are really, they give you the identical physics. And similarly for the Dirac quantization or the Hamiltonian formulation, the two Lagrangians and everywhere the matrices, they were looking different, but they yield the same identical result. This we have checked very, very carefully. And this at the end, I want to give some, for some remarks that I had just mentioned it. I wasn't sure if I would cover it in time. So this shows the correspondence fermion-boson equivalence. So the Dirac Lagrangian really is identically equal to this, where phi is some scalar field, and this is psi bar gamma mu. Psi is the well-known vector gauge current, and which is given in terms of the field phi through this, and this is the axial vector including gamma phi. So this is the axial vector gauge current. This is also equal to this, and this the physics contents of both of them. So but the bosonic, in the past we have studied the several aspects and several variants of the bosonized version of this model in a series of papers, and because of the shortage of time, I did not want to reproduce all those things once again. But in the Slack Spires or Inspire Hep or in our names, you can find all those things. There is a series of papers using the bosonized versions of these models, and I am just close to my, so I think I'm more or less through with my content. So these are the results for the non-vanishing equal time. Commutators equal time means, so here it is x1 x0, here it is by 0 by 1, but by 0 is now equal to x0. That is the equal time commutation. And this is the same, but here we have anti-commutation relations because they are fermionic fields. So the equal time anti-commutation relation, and these last three expressions are identically the same, and this is the path integral which looks algebraically different in the two cases, but yields the same results. So when we make use of the definition of the weak equality, it means it implies the same results. But you can more explicitly calculate the 2-point function in some particular example, or 4-point function or n-point function. You will be able to satisfy yourself that it works perfectly fine. So at the end, let me thank the organizers once again for their very kind patience. I think I have overshot by 2-3 minutes. Thank you all very, very much. Thank you all very, very much. And I would welcome questions if there are any.
You're welcome. So let's thank the speaker. Time for one very short question.
Yes. If you give me 1 extra minute, without repeating Milo's question, I would try to answer his question, that his concern, actually not question, but his concern, that would these techniques be applicable to theories that are non-Hermitian by construction or by definition? My answer to that question is yes.
My question.
No, did I misunderstand? Did I misunderstand your question?
Yeah, very well. Unfortunately, there are no short questions. I mean, the field is too rich and the time is limited. So thanks for your short answer to my question. Thanks.
Yes. Okay, you are most welcome. But Milo, I can assure you that this is really applicable to many wider kind of examples, from 2-dimensional theories, 3-dimensional.
I would propose that you can discuss after closing the session.
Okay, fine. Thank you so much. Thank you so much.
So now we have a coffee break, and you can discuss as much as you wish with the other participants.
Yes, so we are sorry, we are going to miss your coffee now.
Recording stopped.